Hello everyone, welcome back to another video I am titling Understanding Skew-Ts and Soundings. I want to do this video because these tools in meteorology are very fundamental for forecasting many kinds of weather phenomena, especially severe weather, which is what you will see most commonly on this channel. I'll take a high-level approach to these tools and mostly just cover the basics on what information we get and how it is used. The way I have structured this video is I will cover some of the background info on how the data is collected. Then I'll break down the Skew-T and how to read it. And finally, we'll look into an example of a sounding from a severe weather event. If you enjoy this video, leave a like, comment with any questions down below, and we'll get started. And I'm pulling information for the background information from weather.gov/jetstream. I'll highlight the URL up here. And this is a great educational resource. And if you want to get a better understanding of meteorology, this website has a lot of topics that relate to meteorology and can really help with the understanding on some of the topics that are discussed. I'll put a link to this website down in the description below as well. So how do we collect the data we need for our Skew-Ts? We launch radiosondes that are attached to weather balloons. And the radiosondes will collect data such as pressure, temperature, and relative humidity. And so I'm not going to bore you by reading this website word for word. You can go read for yourself on your own time if you wish. So I'm just going to point out what I want to discuss here. And so down at the bottom here, I want to point out there are about 82 different upper air stations throughout the United States that the National Weather Service will launch radiosondes from, 13 of them being in Alaska. So not every single weather office will launch weather balloons, but most of them will on a routine basis. So how's the data that we collect used? So down here lists some of the uses for the data, and the data that the radiosondes collect go into the computer weather models. So this is the input data that forecast models use, and we use that to help make the forecast for a given location. They're also used for severe thunderstorm forecasting, as well as weather, climate, and air pollution research. And also, the data used from radiosondes is also used for satellite data, which will then in turn could also go into the forecast models. So all of these greatly benefit from the data that's collected from radiosondes. So that is an important part to this process. So how is this data plotted? This data is plotted on what we call a Skew-T diagram. Then so here is an example of what a Skew-T looks like. And this may look complicated at first glance, but for those who don't have a meteorology background, there are three main things that you need to be concerned about. And those are going to be temperature, pressure, and the wind staff. And I'm going to go through all of these right now. So first, let's look at temperature. These temperature lines here are called isotherms. And I'll write that down for you here. And so that is defined as lines of constant temperature. And so these lines of constant temperature, or your isotherms, are skewed to the right here, as you can see. And so hence the name Skew-T. That's where the Skew-T comes from. And so these lines of constant temperature, or isotherms, are measured in degrees Celsius. And so I'm going to point out a few key isotherms. Here is the 0 degree isotherm right here. Here is the 10 degree isotherm. And then this would be the minus 10 degree isotherm, so on and so forth. And so next, we're going to look at pressure. And these lines that go left to right, so horizontal lines, these are called isobars. And like the isotherms, isobars are lines of constant pressure. And so I'll point out some of the most important isobars that you need to be concerned about, mainly on this channel. And those lines here are going to be 850 millibars, 700 millibars, 500 millibars, and 300 millibars. And you may recall the relationship between pressure and height. As you increase in altitude, pressure is going to decrease. Generally, the surface is just over 1,000 millibars of pressure, and 300 millibars and higher is the upper atmosphere. And then to the right of your Skew-T is going to be your wind staff. And that is where your environmental winds are plotted, and these show the change in wind speed and direction with height. And so that's going to cover the background info that you'll need to know. And now I'm going to do further breakdown the Skew-T. And so let's take a look at an example from earlier this month, earlier this past month. And this is a RAP model sounding from Huntsville, Alabama. This is one of our short-range guidance that updates hourly, and you'll see these kinds of charts frequently on this channel. So the first thing I want to point out here is the Skew-T in this orange box. So here are our isotherms in your dashed lines here. And these are the isobars in these lines that go horizontally. And so we have our environmental temperature and dew point lines. These are the red and green lines. The environmental temperature is in red, dew point is in green. And so these temperature and dew point lines are plotted as you go up in the atmosphere. And then if you're not familiar with what dew point is the temperature that the environmental temperature has to be cooled to in order to become saturated. So dew point is basically just a measure of moisture in the atmosphere. The higher the dew point is, the more moisture there is in the atmosphere, basically. On the right here, this is your wind staff. These are your environmental winds in this yellow box as you go up with height. And then to the right of that is the pink box. This is where your hodograph is. The hodograph is a graphical way of visualizing the change in wind speed and direction with height, also known as our wind shear. We'll take a look more into this in another example coming up. Down at the bottom in the blue box, here I'll scroll down, this represents the wind shear from a numerical perspective. So the hodograph is more of a graphical way of visualizing our wind shear. The blue box down here is kind of the numerical values for our wind shear. And the box next to this in red is our thermodynamics, also known as the instability. So all of these parameters help meteorologists diagnose and forecast severe thunderstorms, such as what's the likelihood of severe thunderstorms, what kinds of severe thunderstorms are we going to have, what kind of severe weather, whether it's going to be damaging winds, large hail, or could there be tornadoes. And so next we're going to look at what these parameters look like on a severe weather event. This is going to be an extreme example, but let's look at the April 27th, 2011 event. So we're going to look at the evening sounding from Birmingham at 7 p.m. and we'll start with the Skew-T. So the first thing I'll point out here in green, this is going to be a deep moist layer where the red and green lines are close together. So this is red, of course, is the environmental temperature, green is the dew point. And so the closer these lines are together, the more moisture there is in the atmosphere. And so this moist layer extends up to around 2 kilometers. And this is a pretty deep moist layer from the evening of the 27th. And above this layer, we have a region of rapid temperature change as you go up with height, which is indicative of our lapse rates. And that's just a term used to describe the rate of temperature change as you increase with height. So all this shows is that we have a very unstable environment on that day. This is also shown by our CAPE, which is in this column, and this is just another way to diagnose the instability. And we can look into this a little bit more deeply in a different video. And so switching gears to our wind profile, we have our environmental winds here, and this is what we call a veering wind profile, which shows your change in wind direction from east to west. And so these wind barbs here, these are wind vectors. And so the direction that your wind barbs are facing, that is the direction that the winds are coming from. And so here is your veering wind profile in the lowest levels of the atmosphere right here. And so we have southerly winds here at the surface. And then at around 850 millibars, you have winds coming out of the southwest. And then close to 500 millibars, you have your winds that are coming almost out of the due west. And so this is indicative of your veering wind profile and also indicative of strong vertical wind shear. And so next we're going to look into the hodograph. This veering wind profile that we've discussed here can be seen on our hodograph here. And this creates a large looping hodograph in the lower levels. And so this large looping hodograph here is the feature that is most favorable for tornadic supercells. And you can see here also plotted are the wind speed and direction at a given level. So these numbers here that you see here are measured in kilometers. So this is 0 kilometers, which is the surface, 1 kilometer, 2 kilometer, 3 kilometers, 4 kilometers, and so on and so forth. And so the box down here in the middle, these are the numerical values for wind shear, and shown by this column right here. And so that's a lot of information that we covered, and this may be a good video to refer back to as I start incorporating what we've talked about here in forecast videos going forward. It's hard to talk about everything in one video, so I was just trying to hit the high points of what I want to discuss. And so that's going to wrap it up for this video. Remember to leave a like if you learned something, or just enjoy the video. Comment below if you have any questions, or what I should cover in the next video with soundings. And I'll see you next time.